Picture this, okay? It's the winter of 1850 in Russia. The temperatures have completely plummeted to these brutal, record-breaking lows, and they're just staying there for weeks on end. Out in the freezing elements, the Russian soldiers are facing a bizarre and honestly terrifying problem. The solid tin buttons on their heavy winter uniforms are inexplicably crumbling. I mean, they aren't rusting, they aren't breaking from being hit or anything, they are literally disintegrating into this coarse, gray powder just because it's cold. How is that physically possible? How can a solid piece of metal just decide to fall apart?
People at the time actually called this strange phenomenon the tin disease. And it wasn't just clothing buttons. Massive church organ pipes made of tin were literally crumbling to dust as well. To solve this high-stakes historical mystery and truly understand how macroscopic objects can just suddenly fail like that, we have to completely shift our perspective. We need to shrink all the way down to the atomic level.
So, welcome to this explainer. Today, our ultimate goal is to decode the hidden, microscopic blueprints that dictate exactly why materials hold together, why they behave the way they do, and, ultimately, why they sometimes spectacularly fail. We're going to uncover the invisible geometry that literally builds our modern world.
All right, let's take a quick look at our roadmap for today. We'll be looking at 1. The architecture of solids. 2. 3 metallic blueprints. 3. Packing atoms efficiently. 4. Calculating metal density. And finally, 5. Shape-shifting metals.
Okay, starting us off with Section 1, the architecture of solids, building the microscopic world.
So what fundamentally makes a solid piece of metal so solid? Well, it all depends on how its atoms are arranged. All solid materials basically fall into one of two categories based on this arrangement. Over on one side, we have crystalline materials. This is why atoms position themselves in a highly repetitive, totally predictable three-dimensional pattern over really large distances. Think of like a perfectly stacked pyramid of oranges at the grocery store. Almost all metals, a lot of ceramics, and even certain polymers fall into this highly ordered category. On the flip side, you've got non-crystalline or amorphous materials. These entirely lack that long-range atomic order. They're just kind of jumbled up. But for today, since we're diving into metals, we are focusing squarely on that beautifully ordered crystalline world.
Within these crystalline metals, we really like to picture the atoms as solid, hard spheres that are physically touching one another. The three-dimensional array of where these atoms sit is what we call a lattice. But you know, a lattice is massive. To actually make sense of it, scientists subdivide the structure down into its absolute smallest repeating entity, the unit cell. You can essentially think of the unit cell as the fundamental building block of the crystal architecture. It's much like a single repeating Lego brick. If you can understand the geometry of this one single unit cell, you understand the entire piece of metal, no matter how huge it is.
Moving right along to Section 2, 3 metallic blueprints, nature's master plans.
Because metallic binding isn't highly directional, metals really like to pack their atoms tightly together. And astonishingly, nature essentially relies on just 3 primary geometric blueprints to construct almost all the metals we use every single day. The first one is the face-centered cubic blueprint, or FCC. Just look at the geometry here. You have a cubic unit cell with atoms located at each of the 8 corners. But, and here's the kicker, there's also an atom sitting right in the center of all 6 cube faces. Imagine the dots on a rolling die, specifically the one, but on every single face of the cube. In this blueprint, atoms touch one another diagonally right across those faces. This highly symmetrical structure is actually found in some of our most familiar workable metals, things like copper, aluminum, silver, and gold.
Now, let's contrast that with our second blueprint, the body-centered cubic structure, or BCC. Notice the difference right away? We still have our 8 corner atoms forming a cube, but those face atoms, they are completely gone. Instead, there is a single, central atom locked tightly right in the very center of the unit cell's body. In this specific case, the atoms touch along the diagonal, running completely through the cube's interior. This BCC structure is characteristic of your harder, tougher metals, like chromium, iron, and tungsten.
And that brings us to our third blueprint, which is the Hexagonal Close-Packed structure, or HCP. Turns out nature isn't just limited exclusively to cubes. Here, the top and bottom faces are these regular hexagons made of 6 atoms surrounding a central atom, with a little triangle of 3 atoms sandwiched right in the middle plane. This incredibly unique, layered hexagonal geometry is the foundation for metals like titanium, magnesium, and zinc.
All right, Section 3. Packing atoms efficiently, the math of density.
So just how efficiently do these different geometric shapes actually pack hard sphere atoms into a given space? This isn't just a fun trivia question. This efficiency directly dictates the material's real-world density and properties. We measure this packing efficiency in two distinct ways. First is the coordination number, which is exactly how many direct touching neighbors a single atom has. And second is the atomic packing factor, or APF, which is just the fraction of the unit cell's total volume that's completely filled by solid atoms. And when you run the numbers, a super fascinating pattern emerges. FCC and HCP actually tie for the win. Both boast a coordination number of 12 nearest neighbors and an APF of 0.74. That means 74% of the volume is pure solid atom, which is mathematically the maximum possible packing efficiency for spheres of equal size. BCC, on the other hand, with its single atom trapped inside the center, only has a coordination number of 8 and an APF of 0.68, so it's a slightly looser, more open kind of architecture.
Next up, Section 4, calculating metal density, from micro to macro.
So we can actually use this microscopic geometry to predict something we can physically weigh and measure in the real macroscopic world. Let's calculate theoretical density, and we'll use pure copper as our test subject today. It's got that highly packed, face-centered cubic structure. Here is our quick 4-step recipe. Step 1, we count the atoms. Even though atoms are shared with neighboring cells, the math breaks down to exactly 4 whole atoms assigned to one FCC unit cell. Step 2, grab the atomic weight of copper straight off the periodic table, which is 63.5 grams per mole. Step 3, we calculate the volume of that microscopic unit cell using just the radius of a single copper atom, which is a tiny 0.128 nanometers. Step 4, we plug all this into our density equation, dividing by Avogadro's number to scale the whole thing up from individual atoms to grams.
And you know what happens when we crunch those tiny, invisible numbers? We get a theoretical density of exactly 8.89 grams per cubic centimeter. Now, why does this matter so much? Because if you take a solid block of pure copper into a lab right now and measure its real-world density, you get 8.94 grams per cubic centimeter. Our mathematical model, which is built purely on the assumption of hard spheres packed into an invisible face-centered cubic blueprint, predicts reality with just stunning accuracy. The microscopic architecture literally is the macroscopic reality.
Which brings us to our final stop, Section 5, Shape-Shifting Metals, the tin mystery solved.
This is where we bring it full circle, right back to that 1850 Russian winter. We know that the geometry dictates the physical reality, right? So what happens when a solid metal suddenly decides to tear up its own blueprint and adopt a completely new one? Well, this is a very real phenomenon known as polymorphism, or when we're talking about elemental solids, allotropy. It simply means that depending on the external temperature and pressure, a material can actually possess more than one crystal structure. Think of carbon, for example. Under normal conditions, it's just graphite, but under extreme pressure, its atoms completely rearrange to become diamond. The solid state isn't always permanent. Sometimes a drastic change in temperature forces an entire atomic lattice to radically rearrange itself.
So, the crucial point for our mystery is that tin is an allotropic metal. At normal room temperatures, it exists as white tin, which has a moderately tight, body-centered tetragonal crystal structure, but, and here is the fatal flaw, when the temperature drops below a very specific threshold of 13.2 degrees Celsius, or about 55.8 degrees Fahrenheit, that structure becomes completely unstable. The atoms slowly shift and lock into a brand new blueprint, gray tin, which features a diamond cubic structure. And the problem? The gray tin structure is so much less dense. As the atoms rearrange into this new lattice, the metal undergoes a massive 27% volume expansion. Just imagine the buttons on your winter coat suddenly trying to grow by a third of their size. The internal stress is catastrophic. The material literally shatters itself from the inside out, turning from a shiny solid button into a pile of coarse gray powder. The terrifying mystery of the tin disease wasn't a disease at all. It was just a microscopic, shape-shifting architectural failure triggered entirely by the cold.
From a simple pile of dust in the freezing Russian winter to the highly efficient face-centered cubic packing of the copper wires that are probably powering your device right now, everything comes down to these tiny, repeating Lego bricks of nature. The solid world isn't just a boring lump of matter. It's an absolute marvel of precision engineering on a scale we can barely even comprehend. So I want to leave you with this to ponder. If the invisible geometric blueprint of a metal can dictate its very survival, what other shape-shifting secrets might be hiding inside the built environment we trust with our lives every single day? Keep exploring, and definitely keep questioning.